Hello. Hit you already. No, not too early.
Hello.
I'm adding people, yeah. Can I get another sound check? Somebody say something. Trolls.
Hello? You sound
That
good.
works.
Hi.
Sorry, it's always a little maintenance in the beginning here. Oh, here, I'll pause. So I'm recording this. It goes live on YouTube and Twitter in 1 to 2 hours. I reserved the right to moderate, never had to do it. Anything to do with language runtimes and language definitions and typing systems and garbage collection and multi-threading this and that. Things to do with language implementations are all fair game. Otherwise, open mic, except mute when you're not talking so that we don't get too much background noise. And now suddenly a bunch of people have showed up. I'm going to do a little maintenance, and then I'll throw out a starter question, but anyone can throw anything because it's open mic. So I'm going to start because I've been doing something and now I'm getting excited about it. I've been trying to unify Hindley-Milner typing and a forward flow typing analysis. Nice shirt, Mark. That's a good one. And I kind of made progress. So I got Hindley-Milner working on an SSA graph. I'm busy replumbing the algorithm to go from one pass AST to a work list because I'm discovering components of what an AST would be. I'm discovering lazily on the fly, or I'm busily modifying my AST, except it's an SSA form. It's busily getting modified. I don't want to run Hindley-Milner on sort of directly. Let me grab this person here whose names I don't. There it is. And so, so I'm changing the AST to a work list. I've got it in SSA graph already. I believe I'm going to be able to remove a bunch of the funny parts of Hindley-Milner where they say, I have a list of variables which are generative or non-generative, and then he clones the shape of the type at each of the identifier uses, which he then uses basically to imprint that shape. So he's taking a functional body shape, so a map that takes a function from A to B and a collection of A and returns you a collection of B, has a particular shape to it involving A's and B's that are tangled up however they are. Fine. So when you take an identifier in Hindley-Milner and you make a fresh clone of it, you're copying that shape that you then unify. And all the copy does is it removes all constraints except for the ones that are baked into the shape. And when you unify to each new position, you force that shape upon the types at that point in the graph. So, so what I'm doing with this is the important piece here is that constraints only ever add, and I can discover them lazily late. But if I discover them late, I have to reapply them at all their use points. And this is classically what a worklist algorithm does, where if I discover a new constraint because I have further propagated something in a particular function, like this map I just talked to you about, when I go to apply that constraint to all the call sites involving a map, if you pick up a new constraint, I need to go revisit those call sites and reapply the constraint. So this turns into a classic worklist algorithm, which I'm in the middle of implementing this thing. But there's something here that I think I'm going to get my parametric polymorphism and my forward flow typing done almost identically to Hindley-Milner's, and maybe identically into Hindley-Milner's strength, plus also the strength I get out of the lattice forward flow typing, which is different and unrelated to Hindley-Milner, and there's something about unifying them that should be stronger than either one independently.
So are you gathering up the constraints first and then solving them all at once? Or are you doing it kind of on the fly?
Totally on the fly. So the thing that I'm doing with the lattice is always on the fly, in the sense that it's incremental at every possible step, doing, work list one piece at a time, and you're guaranteed linear time and forward progress and an optimal solution by the monotonicity guarantees thrown into the forward flow lattice analysis. Hindley-Milner adds constraints monotonically. And then the assumption is that applying the constraint is essentially constant time because they're mostly small. And this, of course, gets into the horrible actual worst case scenario timing on Hindley-Milners, because they don't have to be small. But if you assume they're small, then reapplying a constraint's pretty damn cheap. And since you're only monotonically increasing constraints, this totally falls into my lattice paradigm, where I'll guarantee you some limited amount of constraint adding before you've constrained everything every possible way, and then you're done. And that turns into the guarantee of both forward progress and optimality and actually efficient forward progress. So it's a more clunky looking algorithm than the AST walk because it's being broken up. But then there's some elegance to the simplicity you get out of not doing an AST as well once you change the constraints around. But then mostly what I'm trying to get out of it is, because I am building what you would consider the AST on the fly from SSA form, like that's constantly being monotonically improved as I hack on the SSA. I can't run Hindley-Milner on a static tree and change the tree and expect to get a similar result. So I have to either keep reapplying Hindley-Milner, building a tree out of the AST, out of the SSA, reapply Hindley-Milner, make some progress, and go back and forth, circle by circle, or I'm just going to do it all in a work list all at once. So that's my giant excitement of the last, 48 hours or something. That and drinking beer on election night, and my wife's finally done being an election monitor, and we're with everyone else, we're waiting around, see what happens, see that the process works. We have a bottle of champagne lying in wait as well, but that's a different story. So did you have something else? Because Trolls, you were the guy I specifically was targeting for this, because I wanted to hear your opinion. Like, do you think there's something going on here that I can do this thing, or is I'm any idea?
Well, I must admit I'm still a little bit hazy on how you managed to combine abstract interpretation and Hindley-Milner.
Okay. Yeah, that's what it's doing.
What do you gain from that Hindley-Milner by itself doesn't give you?
Oh, so the abstract interpretation lets me, for instance, kill dead code paths. So for instance, I can say if def Windows, else if Darwin, else if Linux, and have function calls in the if def partitions that are syntactically incorrect because they say wrong argument counts, and they're just dead. So if I can do any amount of forward flow constant propagation, then I can do forward dead path elimination, for which I don't have to type anything on. And I'm doing that right now. So similarly, if you are dead the other way, you're dead because you're unreached, then I don't care that you mistype. I'll ignore you.
Yeah, that's interesting. So that means, that's because normally the problem with Hindley-Milner is that, as I mentioned, it balances on a razor's edge of tractability. But that extension, by combining with some kind of partial evaluation, which is really what you're doing here, I don't think I've seen anyone try that before and figure out whether that causes any problems, and I don't think it will. I think that's something you can actually get away with without losing the Hindley-Milner properties.
Okay, thank you. It seems plausible to me, yeah. And yeah, that's what I'm doing. I'm abstract interpretation. And I have some very specific guarantees that I'm shooting for, that I want to see interpret out, like the dead code for the wrong side of compile time constants for different builds. That's one of them.
Yeah, the only challenge here is that you have to make sure that when you are ruling out some branches based on your static information, the abstract interpretation, then you have to make sure that no constraints in the Hindley-Milner sense escape from the dead code you eliminated. So
yeah, right.
I mean, if you're careful to do top down, then you won't even you won't ever enter the dead code. But
I'm careful to do it with monotonic properties everywhere involved. So one of the fun things I did with my thesis was combine type equivalence classes with forward flow constant propagation, sort of the aggressive best case one. The equivalence class game basically said that you could do strongly monotonic, optimal, provably closing, efficient, blah, 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 version using equivalence classes. And what Hindley Milner's given me is another version of equivalence classes. They're a little bit different because I was looking for equivalent values and he's looking for equivalent types, which are sets of values, but that totally falls into the same paradigm. So I believe I can make a theoretical boundary here, theoretical argument that's not related to visitation order of any kind, and still allow like dead code to add constraints that will then also be dead and will not matter because of the monotonicity. So I believe I don't have to prevent a constraint from escaping from a dead path. I believe instead it will be the case that it will only constrain the dead code for which is being dead. It has no interesting constraint. So there's no issue with constraining it.
I'm not sure that's true. So let's say that you have a variable x, and you don't know what that's you don't know the type of that yet. You're supposed to infer that, right? So you have your x, and then you have a branch that says if you're on Windows, then x must be an int, or else x must be a string. So something like this.
Right.
And in normal Hindley-Milner, this would be a problem because you have two opposing constraints for x. But in your case, if Windows, that's kind of a compile time constant, presumably. Yep. So in your system, that would be evaluated at compile time, and then this will type, and x will just have a different type depending on the operating system.
Right.
But that means you have to be careful not to let x.
Right.
X
I have an answer for that already because I already thought through that one.
Yeah.
And that one is when I get the two constraints for x must be an int and x must be a string, what I actually end up doing then is I do a meet. In the Hindley-Milner demands a meet of components. When I drop one of the components as dead, the meet shrinks and I lose the constraint that way.
But normally in Hindley-Milner, what you would do is unify x with int inside of the branch.
Yeah, and if the unification fails, you get a type error.
Yes, exactly.
I do a meet instead of a classic unification. That's like, instead of a Boolean yes, no answer back, I get you always a type. The lattice is complete. I always give you a type back. The type may be really junky, such as bottom, which I can't actually evaluate in any context. And that will throw an error later, but it might, it might be able to lift because I lose the dead constraint because I'm tracking the list of people that are constrained as part of the unification. So
actually,
okay,
yeah, that's interesting. So in terms, I mean, normally in old school Hindley-Milner, what you do is you unify x with int immediately when you're inside the branch. Yeah. But in more modern implementations, you actually just collect the constraint x must be an int, and then later on you solve all the constraints at once. And it sounds like what you were then doing is essentially a mix, because those complex types you get out of your lattice, those are kind of like constraints that you then solve later.
Well,
but you also solve some stuff immediately.
I solve them
actually.
I solve them immediately.
Yeah, but you get a complex type out.
Yes, I get a complex type out. Yes.
And that sounds like, and that must be processed later, right? Because then you resolve the conditional, the if windows inside of the.
No, that's part of the continuous evolution of the typing in the graph. So at some point I start saying I don't know anything, and I don't know about if windows or not if windows. So I have to say both sides of the condition are true, or possible. So I pick up the constraint x must be int, x must be string, and I meet them in the lattice. Okay, as soon as I do that, I get x must be something horrible like bottom. And at this point, that's the state of the lattice, but I progress on my partial evaluation. I lift the if windows to something more reasonable. Let me pick up. Then I picked up two people in a row and I missed one. And Hidinga. Let me get him in here. Sorry. Yeah, and so I come back to the work list and I decide Windows is true or false. So I reevaluate. It becomes one of the branches goes dead. I go pull that branch off the work list because I throw the branches on the work list. I throw the whatever branch on the work list. Okay. He decides he's dead. He lifts his own type from int to top because that's what happens for dead. That unification remains, but I unify top with string and I get string and I'm all happy.
Okay, then I have a more complex problem.
Yeah, throw it out there.
Let's see. Okay, let's say that you have a binding. I don't know what let's see. Var x is
You don't have the keyword var. You just say x equals.
Yeah, okay, but just
but
I would normally write let because my function programmer. So let's say you have a definition of a variable x, and the right hand side is going to be a type error on Windows somehow. But that's also, and then you have a y that is a type error on Linux.
Yes.
And then later you have your a branch if is Windows, then use x, else use y.
Yeah, type errors are well defined in the lattice. And so I get a unified type error of type on Windows, to error on Windows, or whatever the error on Windows unified to error on Linux is. There's a meet, they're an element in the lattice. I can meet them. I get another element in the lattice. It's complete. So I have an error in either case here. So the result of that expression is a type error of some kind that is, until I know what Windows is true or false, it is a type error that is the unified worst case of Windows and Linux.
Also this should actually be the other way around. The point is that var x will only be okay to use on Linux, so it should be this way around. Sorry. So the thing here is, can you remove this dead code, even though it's kind of not, it's dead for non-local reasons?
So okay, so if Windows use Y, which is fine on Windows, yeah, this works. Like I said, the lattice totally holds on to error conditions, sort of in every kind of abstract incremental way.
So what you mentioned a worklist algorithm, and this would work if you just constantly retype checked the program until you reach either a final error or
yes, I retype. Yes, so there are two things to do with the lattice thing here. Two directions to go. There's an intuitive one that's easy to explain. There's a counterintuitive one that's harder. One's bottom up, one's top down. So there's an optimistic and pessimistic. So the pessimistic bottom-up version is I start from a ground state that I get constants and I build continuously until I hit a fixed point. I can't get any higher. This model says that the program that I've partially evaluated is that everywhere always some correct state, but I'm lifting. When I say correct state, I know the type of everything, and the types are correct even if it's a type error, because type error is not a fail, it's just another member of the lattice. That only goes so far because there's an optimistic or a top-down version which gives you a monotonically better answer. The top-down version goes the other way and says everything starts at top and falls. Both of these algorithms, the top-down one, the falling case always lives in this state of ambiguity until it fixed points, and then it's done, and now you have a correct set of typing for everybody that will be monotonically bigger than the bottom-up version. So both these directions are possible. I'm going to have to do the top-down one. I do the top-down one before I declare I'm done with typing.
But your type checker is basically a fixed point iteration.
Yes, and it's a top-down fixed point iteration. Yeah. I do the bottom-up one also because it's cheap and it's easy and it's fun, and you can read in 99% of things just type, and I can stare at them without doing the funny algorithm.
It's pretty crazy. I mean, in a good way. It really is interesting. It's like the way you normally do compiler optimizations or compiler analysis lifted to the type checking level.
Yes. Well, that's what I did with, C2, yeah. I did that. Basically, I strongly typed IR using a classic compiler optimizer, and I discovered all these fantastic old type things.
Yeah, but to me, C2 is a compiler backend. I know maybe that's not how you thought of it, but you usually don't, as a user, write code that directly targets C2, do you? It goes through the Java front end first.
Yeah, I just started with Java bytecodes as a language and then said what I can infer for types. The answer was everything. And so this AA was intended that was one of my main design goals, was to do lattice 3 typing, to do the type discovery and see if it made a difference, if I could do something exciting with it.
Actually, what you're doing reminds me a little bit of these fancy dependently typed languages, which do arbitrary type level computation at compile time before they type checks. So they inline stuff and just to see if it type checks.
What was that?
It reminds me of dependently typed languages like Acta and Idris. So they are kind of the academic cutting edge of type theory. They have Turing complete type systems. And code theorems in type systems.
Right. I'm certain my type system is not Turing complete.
No, it just reminds me because they also
Yeah.
do a lot of evaluation and fixed point iteration kind of in the type checker to try to massage the program into a form that is then type correct.
Yeah, okay.
So it's not the exact same thing at all. It's just philosophically related, I think.
Interesting. Can you throw some of those languages in the chat?
Yeah.
As always, I'm like.
So Idris is probably the one that's easiest to understand. It's also mostly like a programming language.
Certainly related, because a lot of what he's doing with the lattice is kind of eliminating. It is kind of like some of the dependent types, in that he's eliminating. Like with a dependent type system, you actually know what range the values are in at any given point, right?
Yeah, I have fine-grained values for types. Like there's a notion of an int, but actually it's a lot more fine-grained. There's an int 8, 16, 32, positive.
Oh, yeah. But with a dependent type system, you know on line 17 that it's either a 3 or between 8 and 11 or negative 72.
I know that as well. Yes. And I wouldn't have said, I never heard the term dependent type system. I guess I have, I just know anything about it, but yes.
Well, keep in mind that my academic credentials are negative. So
it's all good.
It's just what I've read online.
Well, okay, now I'm strongly encouraged. I'm going to carry on. So thrown into the AA GitHub, the top level, there's a HM blank HM12. HM1 is a clone done in Java of somebody's, gosh, what would they write it in? They wrote it in, let me go find it. There are some versions that are just implementations which are just based on somebody's Scala version that I just, so if somebody wants to look at a Hindley-Milner that's very straight up, very plain Jane, hm.java and hm1.java and test hm1.java are very plain Hindley-Milner, just by the book. And then hm2 is the version where I stripped the discovery of unique variable names and their scopes out and just said I have SSA and unique names already. And then hm plain is my current hackable version. I'm doing this is no sea of no's now, but I'm just turning it into a worklist algorithm with some very simple, obviously requires Hindley-Milner level typing to go type it if you want to go stare at code. But the hm.java is like mid getting regutted.
Where is this? I don't see it.
AA source main Java AA HM. Yeah, source main Java. Oh, concliffe C AA hm.java. hm.java is mid hack. I would go to hm1, which is like just a Scala clone, a Java clone from a Scala clone, from a Perl clone, from a paper from, Cardelli or whatever. I don't know the name right. Do I have a link? I can get you a link. Yes, I have a link. I took a horrible, long denied Windows forced reboot, and now all my windows are smashed and I have to rebuild them all, and I hate Windows. I don't know what the hell I'm still in this thing for. Source main.
Is Windows a language? I've never heard of this thing.
I'm sorry, what now?
Windows, is that a language?
No, it's an abysmal nightmare that I've been unable to escape for years upon end. Oh, under Hindley-Milner, the branch. That's probably what you're missing there. Okay, so HM1 is plain Jane. HM2 is
And before I forget, I do want to hear more about this worklist thing that you did.
Oh, yeah.
But cue that up. Don't jump there yet.
Okay, I'll start reading about Matt's. I can cover that, Matt, in a minute here. It's not. No, let me come back to that one, because that one I have to go sort on. So the worklist thing is just it's the sort of common denominator on these kind of algorithms. Once you start from a monotonic, a lattice that's commutative, distributive, associative, complete, bounded, blah, 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 like every buzzword on the planet, fucking lattice. And you have a bunch of transfer functions that, given elements of lattice, produce a new element of lattice, like an add, takes an int-like thing, and an int-like thing produces a new int-like thing, but there's some refinements because you can add 0 and you can do +1 and out of bounds for int 8 versus 16, blah, blah, blah. And same for every possible, primitive on the planet, including memory and loads and stores. So you have some sort of lattice, you have some transfer functions that are monotonic. Immediately you get a worklist style algorithm that is provably optimal and provably linear time and provably incremental. It's incremental bottom up, always correct. We'll only find better types for things. And it will top out at the lower bound version. That's the bottom up. The optimistic one is called constant propagation. It's the classic constant propagation algorithm. There's a top, there's a middle thing and a bottom, and you do, okay, that's what I'm doing, except constant propagation on steroids. Now, conditional constant propagation, all I did was I threw in control as on or off, also in the lattice. And so that becomes totally conditional constant propagation as a classic thing using straight up lattice. Now, my lattice has got more butch to it. So I do memory contents, I do function pointers, I do closure types, I do, all kinds of other fun things, arrays and struct discovery of names of structs and field offsets and contents and yada, yada, everything on the planet. But that's the same theory holds. If I can squeeze in structs and field names and struct discovery into a lattice format, I can discover them all using the same worklist algorithm. So basically I have a big ass hammer and I'm making my hammer bigger and I'm hoping everything looks like a nail.
So what specifically do you mean by work list?
Okay. So the bottom up version says I've built an SSA graph to start with. I initialize everything to the bottommost type, which is always an error. I then throw everyone on the work list to start with. And then I pull something at random off the work list. Doesn't matter which one I pull. I evaluate as types. So if you're a constant 5, I evaluate you to a 5 and you lift from bottom to 5. That's a lift. So this operation is monotonically lifting. So the transfer function monotonically lifted. And then I put the neighbors of 5 on the work list. So I have a graph. So I just do a neighbor check, throw them on the work list. Lather, rinse, repeat. Pull off the work list, evaluate the transfer function. It only lifts. Put your neighbors on the work list. Repeat until you quit lifting. The top-down version works identically. You just put everything in at top, and then you fall monotonically. And the transfer functions are completely identical and ambiguous, whether they're lifting or falling. They don't care. They're just monotonic. So the bottom-up version has the case that if I stop this process at any point, my types are correct, but perhaps pessimal. I can maybe find better. And if I have things left at bottom still in the typing system, then I have an error that I can't evaluate. I claim programs and everything. Yes, the work list approach. Yeah, exactly. If I do it top down, I cannot stop in the middle because I may have optimistically made choices that are not valid yet. And I can't prove they're valid until I come to a fixed point. But once I come to a fixed point, I'm done. The answers are all correct. And then if those types are also not bottom at the fixed point, then I don't have a type error and I have a thing. So that's the bottom up, top down work list. There's a variation of the same theme where the work list is more complicated, where you do value equivalence between nodes in SSA graph. Standard value numbering is the bottom up approach where I simply do a hash of the opcode and the inputs in the graph with another hash to somebody else, the same opcode, same inputs. Totally classic value numbering with a hash table. There's a top-down version of the same thing where the work list got more complicated. And that was my PhD thesis. Fine. But the theory on how it works, it remains the same. As long as it's monotonic, the transfer functions are all monotonic. You get this behavior that it closes to a fixed point. And in fact, it closes to a fixed point in a bounded period of time, and that's linear in the depth of the lattice. So then the other thing I'm doing is I'm doing general graph rewrites. And the general graph rewrites also run off the work list, except that in order to do them sort of optimistically top down, I need to have the one-step Church-Rosser property, which I don't right now have. I know how to get there. I don't have it. That's a piece of work I haven't sorted my head around. It's just like a giant ass piece of work. So it is the case that my bottom up approach does things the top down one can't do because it does graph rewrites. And because I don't have the one-step search roster property, there is a theory that says there's an order evaluation where I'll get a different answer because I will discover something on one kind of graph rewrite that I can't discover if I rewrite the graph in a different route. At the moment, I'm very strongly normalizing, so I don't have any instances of that, but I don't have a proof in place, even a mechanical one, even just an automated testing setup in place that says there are no failures, which I need to have before I can claim I have one-step search roster. So that's sort of where that piece is going. But yeah, it's everything's done on a work list. A work list for everything and everything for a work list. Fine. And then because I have the other properties of monotonicity and bounded lattice, I have guaranteed rapid convergence and all that kind of stuff.
Yeah, the reason I was curious is because it sounded a little bit like
this is almost surely the correct page.
It sounded a little similar to how we handle AST processing, which is a technique I've never used or seen. So I was curious if it was similar. Because what we ended up doing was basically breaking down into a larger number of stages than a traditional compiler would use, and then relying on some of that monotonicity to allow eventually concurrent execution of the compiler stages, but more importantly, allowing circular dependencies to be resolved in arbitrary orders. So sounds like a similar concept, but from a different, from a completely different end of the universe.
Yeah, I'm sorry. My apologies. I was busy reading papers and you were telling me of an analogy and I half heard it and I half didn't. I'm sorry. So I can't listen and type at the same time. So I'm listening.
No worries. No, I mean, we have a multi-stage compilation process against an AST, and the traditionally, any compiler I've worked on previously, if you couldn't make progress on a particular branch of the AST, it was a compiler error, and you either abandoned that leg of the tree or you abandon the compilation altogether, right? So it's for particular language reasons, in this case, we didn't have either of those options because there could be a correctness that simply remains to be discovered at a particular point in the compilation. So the idea was at any point, and it's kind of like this work list concept. At any point, you've gotten there because the things that you depend on have already emitted enough information for you to be at that point. So if you can't make progress, you can always wait for one of the inputs to change, so to speak. So kind of a similar concept, and it solved the circular dependency issues with multiple modules having dependencies on each other such that they would have to be compiled together. So
right, as soon as you ran them together, you had to run round and round and round between them.
Right. But the other benefit of it was it also allowed for it also allows for, we haven't implemented it yet, but it allows for the compilation to actually be spread out across any number of threads, any number of cores.
Yeah, back in the day, a lot of folks beat on me to make C2 more parallel for faster compilation. The issue with an SSA graph is, or parallel modification of the graph, is that you have a neighbor collision problem, and the overhead of guarding against neighbor collisions at that time, that era was 20 years ago, exceeded any valuable concurrency I was going to get out.
It's a lower,
big chunks of the graph were independent.
Yeah, exactly. So if you have large graphs, large enough graphs with enough independence, then you can actually, because I'm talking about more of a tree form than just an arbitrary graph form, I mean, you could be processing fairly significant sub trees.
Yeah.
in parallel.
You have to claim something at some point and then process, and you claim a big enough piece where you have a natural place to claim a large enough chunk of work to make it worthwhile.
Well, I think the work list itself is the claim.
Okay.
Because you took something out of the list, you own, until you put it back in the list, you own the work.
Well, okay, there's a separate list there or something. There's things that are not on the list because there's nothing to be done with them.
Right.
Everything on the list has something to be done.
And because you're in an AST, there's nothing to be done because the next stage in the AST starts at the root.
Yeah, yeah.
So you would only have one thread, and then when it branches, you could have, if it defers one of the branches because it can't make progress, that goes into the work list, and then it follows the other branch. And if it
Okay, yeah, no, it's a little different here. If I have something that I can't make progress on, I don't put it back on any work list.
I see.
Because it may be done. That may be the limit. It gets on a work list if a neighbor changes. Unlike an AST, I have nearest neighbor information. So anytime anybody makes a change, I can nearest neighbor throw you on the work list.
Mm-hmm.
But on the other hand, that means when I go pull something off the work list, it doesn't implicitly include a tree underneath it. It's just the node. Typically, the evaluation function, the transfer function, involves some subgraph around the node that I need a consistent read on. And so I'd have to lock some region that's arbitrarily different for every abstract interpretation function.
Right.
Do the math, update the 1 point, and then release the lock. That might be made efficient in a way. I don't have it in my plans right now.
Well, it's also fundamentally, I mean, your approach appears to be infinitely natural for a sea of nodes, right?
Yeah, well, that's the point.
Yeah.
Well, yeah, no, that's fair. You know, back in the day, I went back and forth between these algorithms for their classic data flow and tuples, and kind of rounded around till there was an obvious beneficial feedback cycle to work list and SSA graph, and then just kept refining the graph notion so I could jam more and more stuff onto the work list.
I've got to eventually write one of these sea of nodes compilers so I can actually understand some of these ideas that you're talking about.
What the hell's going on with it? Yeah, fine. Yeah, do it. Here, I'm busy modifying the AST from a standard Hindley-Milner like toy example. These are toy examples, functions where you hand write the AST as a new tree element, new tree, and you nest the fucking, code. That's your tree. So you build an AST by hand. So I'm busy like whacking that around into a graph so I can run my toy Hindley-Milner algorithm on a graph to validate that I get the same answer out versus the tree, right? But at some point I'll have two pieces of code that are both implementing HM, one of which is classic AST tree walk and one of which is here's a graph. They're going to be tiny, one file with a couple hundred lines, no more than, and maybe it'd be a useful like exercise to stare at that.
Yeah, no kidding. I will stare at it.
Yeah. Well, the ones there now, it's just Hindley-Milner from Java. And then value-dependent types for matrix IJ. This is Matt. This was like size for matrices. When you say matrix IJ, IJK are compile time values you want to prove are equivalent, but you don't know. I'm asking a question, but you don't know.
Yeah. So you can only multiply matrices when the number of the rows and the columns.
Matt, or everyone else is very quiet.
How about now?
That's great.
All right. So you have a matrix I rows, j columns, and then you are multiplying this by another matrix, which has k rows and.
Yeah. So you don't know I, j, k, but they're
exactly. But you know that they are the same. You know that the latter matrix is going to have the same number of rows as the first matrix has the number of columns. And in this case, you can multiply them. So this can be useful to me in my previous life when I was doing number crunching in C++. That's where it was really useful to have templates which can have value parameters. So in C++, you can express that you have a matrix which has k rows, j columns, and you can overload the multiplication operator, so it only takes conformable matrices.
Right.
But in C++, it would have to be a constant at compile time eventually.
Yeah, which is totally fine. Which is totally fine for a wide range of models. So if you have something which is a very specific set of model, when you have, say, 15 parameters, and you always have 15 parameters, then you have another model which you always have 12 parameters, and another model when you always have 16. It is very, very, very common in econometrics, for example, and in a lot of statistical models. Then it's very frustrating that you cannot express this in languages like Python or R, because you know it will never, ever change for the entire lifetime of the model. It is often a defining feature of the model that it has, say, 15 factors, and every one of those factors has some specific interpretation. So it's very useful because there's a lot of computations that you do later on. For example, when you estimate the model, you have to put it through a numerical optimizer, which is going to perform a lot of linear algebra operation. You are also going to maybe compute standard errors, which are going to perform matrix inversion and pre and post multiplication. And these are very, very commonly hard to get right routines. So
Yeah,
when you're
right.
writing your models and your own optimization routines, when you sometimes have to do, then it is very frustrating that you run the optimization routine for half a week or so, and then one matrix has the wrong number of rows and it all crashes. So in C++, even though I had almost no reason to do this, because everything was expressible as matrices and vectors, so I could program at high level, I get pretty good speed with some NumPy. I still wrote it in C++ just for the glue code, because I wanted to have type checking in the glue code.
Yeah,
So
totally.
for productivity, basically, not for performance, but just for productivity.
Yeah.
So do you know how many languages try to address this? I have an interest in it myself because I'm taking my own swing at it, but it seems like something that more languages or libraries or whatever should be trying to solve, because I've also heard that people get these size errors after days of execution in dynamically typed languages.
Yeah, I'm curious myself, because oftentimes you don't seem to have that much in between. What I'm thinking of is there's this C++ area, which is restricted to constant. And then whenever you look for more theoretically based approaches, you immediately hit dependent world types. Like you immediately have full flexibility for proof carrying code that can even have runtime values. Like Idris too. Idris definitely can express that, but Idris is not exactly a mainstream language. It's not that easy to implement, I think, on top of any existing mainstream languages, like adding this to Java, for example.
Right. So I actually, in my language, I took a swing at trying to handle this. So I have an example here of a small, very, very small linear algebra library where you can express these constraints. And the limitation is that the constraints can only be variables or constants. So it's not full dependent types. But for example, you can express the constraint on matrix multiplication. But for example, you cannot express the fully general Kronecker matrix multiplication because the sizes of the result are not just exactly the same as the sizes of some of the inputs. They are sort of, you multiply together some of the sizes, and that you cannot express that.
Right. I think that's an interesting area, even looking into those somewhat simplified constraint, but still useful and productivity enhancing approaches. I think that there is some interesting space here.
Yeah, I've been meaning to do some real research in it. Right now, we just done an implementation, and we kind of got lost in trying to formalize it. But I think there's room for a kind of, it's a poor man dependence type, really, where it's much simpler than dependent types, which also means you can give better errors and so on, and explain to users how it actually works. But there are many things that you cannot encode directly. I mean, complex cases you cannot encode, but you can code these kind of things, sizes that must match exactly. That you can encode.
Sounds interesting.
Well, it's also interesting because it's probably more practical. Like, you know, when you look at some of the conversations on some of the, what is it, Idris or whatever, it's like people spend more time trying to prove something than it would take to write an entire language to implement it.
Yeah.
It's
especially Acta is more of a theorem prover. I think Idris was originally designed to try to make a practical programming language that has dependent types. I mean, that's still quite challenging. And it also turns out that dependent types are really hard to compile efficiently. Normally types are just a compile time thing and they go away. But for dependent types, you often have to keep around a lot of the types at runtime because you can embed size values in the types. So you might need them. So Idris discovered this, and then they added an entire new layer to the type system where you can then indicate, well, do we need this type at runtime or don't we? And then you can reason about how expensive the types will be. So
wow.
that I think is the state of the art in trying to make dependent types practical. I mean, they're still difficult to program with, but now they can.
Because one way to look at dependent types is to almost, from a traditional. So I'm going to state something that seems disprovable on the surface, but I think you'll get the idea. You could look at a dependent type system as being implementable today in any type system if you simply consider that each potential value is itself a subtype. Instead of thinking of it as an instance of a value, you could think of it as a subtype of what the instance would be of. And then what ends up happening, of course, is that you have an infinite explosion in types at that point. So it sounds like what you're talking about with the ability to figure out which ones are needed and not is that from a practical perspective, you can either fold or discard the vast majority of those potential points and or areas in the type graph.
Yeah, that's the idea. Because otherwise you end up with enormously inefficient code. It basically it's an American type code, even though you have a super advanced type system. And that's not great.
There is one interesting enhancement there is in C++20. So it used to be that those parameters could be only simple values, like you'd have a matrix of 5 rows, or you would have a matrix 5 rows, 6 columns, but now it can be also constant objects, which could be also strings, for example. And pretty interesting example is the compile time regular expression engine, because you can pass it a regular expression at compile time, and it's going to be compiled into a very efficient state machine only for that specific regular expression. And what you are passing, the regular expression parameter itself, is basically this compile time object. So it can lead to a pretty interesting code in applications.
So that means you have to express a regular expression parser in C++ templates?
Not templates anymore, it's constexpr. So constexpr looks like regular C++ code, you just slap constexpr in front.
Does that mean that every C++ compiler also needs to embed a C++ interpreter?
Yep, it used to be in Clang. They are changing quite a lot now, because it used to be an AST worker, which is not very efficient. So I think they are currently designing basically a bytecode, and they will be interpreting C++ bytecode at compile time. Why they need a VN if you can do it all at compile time?
Then they're going to create a JIT for that. And then after they have a compile time JIT, then they'll have a hot-spotted.
Sounds perfectly reasonable.
Do, right?
Well, I don't think C++ is done until every single language feature ever thought of.
Yeah.
Except garbage collection, that's too exotic.
So Charles, the example that you posted, that's not part of your language yet, or it's something you're working on?
It is. No, it is part of the language.
Okay.
We just haven't written a paper about it yet, so I cannot tell you exactly how it works. Well, I can explain it, but I cannot point at any explanation of it.
So when you say we, this includes some of your students as well working on it?
Most of my colleagues, we haven't really exposed students to the formalization of this, but we are pretty sure it can be done by a fairly simple extension of Hindley-Milner, because that's how we implemented it. So now we just also need to show on paper that it works, not just in code.
Cool stuff.
And the basic trick, if anyone here knows about Hindley-Milner, is basically to treat sizes like you treat type variables, and then do roughly the same kind of inference. And that's basically it. It was surprisingly easy. Then there are some edge conditions you have to take care of, but the basic idea is just to extend type inference to size variables instead of just type variables.
Yeah, that's kind of what I was trying to describe before, is that you could treat, like if you treat list of T, of some particular T as a type, you could treat a specific size list of 2, T as its own type as well, right?
Exactly. So that for example, in the dot product here in the link I posted, that NT, so the N in braces and the T, that's a type of an array with element type T and size N, and the N is just in this case, a size parameter to the dot product that's to the left of the colon, just like you would otherwise have a type parameter. But it's so arrays can be seen as a 2-argument type constructor. You give it the size and you give it the element type.
That's what I'm implementing as well.
Cool.
Yeah. I don't know how well it works when arrays are not built in. I mean, we're really exploiting the fact that our language is very small and arrays are a special thing. And I don't know how well this would work for user-defined aggregate types. Then you probably need full dependent types. But for a special purpose language, this is very simple. And we've exposed it to students. I mean, we've had students program with this and random people program with it, and they can figure it out. So I think it's understandable.
And do you support ranges as well in those sizes?
No, not yet, because then you actually need to do arithmetic at type checking level and have an integer problem solver. And we wanted to avoid having a sat solver in the type checker.
Yeah, because that has interesting side effects from an optimization point of view. If you can aggregate the ranges within as you roll it up, you can then pick arbitrary machine types. Not arbitrary. You can pick machine types based on the expected ranges and potentially pick different algorithms based on.
It's not machine types, algorithms, or it's blocking factors for doing our
Right.
multiplying stuff vary by cache footprints and the like, register counts.
So for next week?
Yeah. Suppose we'll have it ready for us next week. Yeah. I thought I was going to be further along this week, but I got sidejacked by the election. So it's all fine.
There was an election in California?
Yeah. It went smoother than in some places, yeah. But there was a lot of work involved. So. And not nearly as much screaming and yelling, but enough. We have our share of loonies here too. It's all good.
So inside of a C++ constant expression, can you then use more templates and constant expressions? I mean,
Are you asking if you can nest them?
Yeah.
Yeah, you can have a function calling a function. Recursion, for example, works.
Yeah.
What happens if they don't terminate?
The template expansion doesn't terminate. I've seen a guy do a prime number generator using prime numbers for the error line number using templates.
That was the original application, yeah.
Yeah, that's templates, but this is constant expressions. What are the rules for those? I haven't used C++ since these were
They cannot be undefined behavior, and that's actually pretty cool because you can have compile time detection of undefined behavior if what you're doing fits into compile time. Let me see if I can find that. That was actually pretty interesting.
That makes sense.
Just don't have any undefined behavior. Fine.
But well, it doesn't detect everything, right? I mean, some parts of undefined behavior would be expensive to detect.
So, yeah, I pasted a link, and this is pretty comprehensive article that goes for every single undefined behavior that is possible to check at compile time. Of course, you have to know things at compile time. So if it's a division by constant 0, for example, then it's fine. But if it's a division by random variable x, then that's not going to be compile time expression at all. So it only works for compile time expressions.
Well, I'm also thinking about, so does C++ have the restrict on pointers yet?
Not in the standards, no.
Oh, okay. Because, yeah. I'm also thinking about, what about undefined behavior that are kind of non-local? Like, for example, in C, you cannot, if you actually violate the restrict, so you have aliasing, then that's undefined behavior. But that would be really expensive to check in an interpreter, because then you basically need to check all pointers all the time.
Right. I'm actually wondering what is it going to be on the side of LLVM, because they, to my understanding, I'm not involved in this part, but they're also currently working on expressing aliasing restrictions, which is basically what would enable to implement restrict. And semantics for this still has to be defined. I mean, there are checkers for LLVM IR, like the work by John Reger from Utah, for example, that rely on having formally defined semantics of LLVM IR operations. So it would be very convenient to have also well-defined formal semantics for the aliasing restrictions and no aliasing restrictions in LLVM, because then you could check compiler optimizations for correctness, basically. Not sure how advanced is this work, but I do know that there is some work in this area.
I got out of the C++ game a long time ago. Hotspots in a very narrow subclass of C++. And everything else, it just kept adding humps on the camel. It's fine.
Well, I mean, some additions are removals in a sense. For example, you don't have to care that much about template metaprogramming once you have constypes, and you can just write regular, normal code to have compile time computations. I think that's a nice change. That was never a pretty syntax, and it was not easy to read.
Yeah, so in AAA, it's just because I'm doing partial evaluation, all those constants become constants. They're up to the limit of partial evaluation. And you don't have to deal with the different language syntax left or right. It's fine.
Well, actually, so when you do partial evaluation, do you do it greedily? I mean, is everything partially evaluated as much as possible?
Yes.
What about stuff that's inside of a branch that you cannot evaluate the branch condition at compile time? Maybe there's an enormous loop inside of that branch that really you should not.
Well, so partial evaluation here doesn't do anything that runs infinitely. So you said greedily forever. No, that's not what I do.
No, but I mean, it might be an enormously expensive loop. I sometimes write programs that take no input. So in principle, they could be evaluated entirely at compile time, but they check something really expensive.
Right. So I don't evaluate the fixed point. I don't evaluate the loop to its conclusion. I evaluate it to a lattice theory value that's a fixed point, which is typically one pass through the loop. The same pass I did when I was parsing.
Okay, because the fixed point just becomes the top type or whatever. Yeah, something.
Yeah, it becomes whatever the fixed point of the loop is. Right. It's not top. It'll be some bottom-ish thing. You're computing a Boolean of whether or not this is a prime number or this is a Fermat's last theorem is true or false, right? You have some loop that runs forever. I just take the back edge, say, I don't know, meet it with the top end. You fall to int or Boolean true false or whatever the hell it's going to be, and I'm done. Right. So
in other words, you glean as much information from the loop as you can determine from both the entry and the various exits, given that you know inside the two that it is capable of running more than once.
I run a conditional constant propagation algorithm, as we've much discussed here, on that loop, which guarantees me that in a handful of passes over the loop body, by the depth of the lattice, I'll hit a fixed point and I'm done. That is part of the typing system, but it's also just what an optimizing compiler would do.
Hey, Matt, I have a request. Do you have a link on this fixed point concept?
Oh, the Google
wiki should the static program analysis book, it's pretty good. Just a few links ago.
Cameron, the easy answer is if you were to solve a system of equations, like a 2x2 high school algebra system of equations, and you get an answer out, that's a fixed point for the system of equations. Totally what I'm doing here, I can express as a system of equations that I solve, and the solution is the fixed point.
High school math is something I actually did.
Right. Okay. So this is done in a different space than linear numbers. You know, it's got this lattice theory going on, but it's the equation solving is almost completely identical. And the fact the whole graph worklist thing is provably symmetrically equivalent to doing however equation solving you want to do. So it gives you a fast, efficient way to do equation solving for equations that have the right properties on how the variables are defined. Static program analysis, what is this? Teeny imperative language. You want, but there's fixed point algorithm. I see that, but pull up fixed point. Oh, I see. Pull it off the wiki here. I bet the wiki's got. I can type it here. Many meanings. Okay. I'm going to go honestly with number 2 here. I'll throw this on the thing. This is not, there's a mathematical version. I am symmetric with the really mathematical version, but the notion of a numerical solution where you run to a fixed point for me was more intuitive, understanding what it was doing. Now, these guys iterate, the numerical ones iterate closer and closer and closer, and they have sort of asymptotic reduction, and the mathematical versions that I'm doing stop, they make hard steps, and then they stop at I'm done. So it's not a asymptotic approach, but I found, for me, the mathematical version more intuitive to get started on it, but fine. It's the same basic concept in the end. I guess the other piece is that the top-down version gets you a higher fixed point. And that's sort of that was a little more difficult to wrap my head around. Yeah, this is a really recent paper. Mostly it's like how much you want to do with language. Yeah, fine. Procedure round robin. Set everyone at bottom or top or whatever. Yeah, some at bottom. Wow, everyone is not identical. Recompute. Yeah, that's it. And then there's an obvious, I would claim obvious optimization pieces that go on here, but you're probably talking it through already. Choose non-deterministically from. Yeah, right. I can do that. What? Oh, yeah. Sorry. Come on in. Got cold suddenly. My cat has to knock at the door. Yeah, I got company. No, go get. No, don't go find Mama. Don't bug me. Go find Mama. Sorry. Hey, Lisa. Oh, she's out somewhere. So here's my 25-year-old cat somewhere, we don't know how old, who's going from gray to white, getting needy in his old age. It's fine. Propagation worklist algorithm, transfer functions. Yeah, section 510. Where are we in here? Oh, that's 3. I need to go back to the title. I should. This looks pretty reasonable, honestly. Yeah, widening. Oh, okay. He's hitting all the fun points. Right. Okay, I will steer more later, but I'm doing what this guy's doing like everywhere and all the bells and whistles. Yeah. So I don't know. I got this stuff 25 years ago from other folks. But it wasn't maybe thought through as quite like constant propagation itself was known to be doable as a work list. Most other folks just did a batch pass for a particular optimization. And I kind of feel like I pushed hard on the work list approach and kept adding more things that you could do on the work list. But I didn't go academic other than my thesis. If you're doing anything else in here, any other tricks? No, then add blah, blah, blah. Now it looks almost identical. So the recent thing I'm doing, I'm running the work list both forwards and backwards. I can run backwards flow and forwards flow in the same work list at the same time and get the same fixed point algorithm, same optimistic, better answer kind of things. But the only backwards flow I'm doing is liveness, so it's not terribly exciting.
Are you by any chance doing this for partial redundancy elimination?
Well,
that's one where it comes up when you iterate bidirectionally, at least in the standard.
Yeah, so I looked hard at PRE a long time ago, comparing PRE to my work list with global value numbering as a hash function on the opcode and edges on the graph. And the answer came back was that with the partial valuation, the global value numbering, the constant propagation, it was not equivalent to PRE. They each got something the other didn't, but in practice, like it was hugely better to do what I'm doing. So the additional gains that PRE would give over and above what I'm doing now are sort of trivially small. So I'm not excited to do PRE. It doesn't buy me anything.
Right, fair enough.
And in fact, we can go look at where it wins, where I lose, and the answers always come around to values that are partially alive on certain branches that I can't declare completely equivalent for whatever reason, but I get all the obvious cases sort of obviously in the obvious way, and suddenly the leftover corner bits that I don't get become sort of vanishingly small. I went through this effort some years ago, and I repeated it more a decade ago again, and the answer came up the same. PRE doesn't buy you anything. Wow, it's pretty quiet here now.
Too much reading going on.
I know. Well, this is actually a well-written paper. I'm liking it, and I'm just glancing through. Or at least he's touching all the points that I thought were important on how these arguments all go and why it works and why it's efficient and fast and yada, yada, yada.
Yeah, but he's not using that 2-column paper format that's so popular.
Yeah, fine. Honestly, I think it's fine in terms of his.
It's essentially, it started as a lecture notes. I think it's for his course at Aarhus University in Denmark. So
who's the author here?
One of the authors is Anders Müller, Danish pronunciation, and that's actually my alma mater, Aarhus University.
Ah, okay.
Huh.
Da-na-na. Teeny imperative programming language. Oh, I love it. Yeah, I have my take on how small a programming language can be for teaching people. It can get pretty freaking small.
If you want to get real, not sure small is the right word, but let's say basic, you can always teach people brain fuck. I mean, it's about as basic as it gets.
No. Well, something that's sort of legible, at least a little bit.
Hey, that's probably the best way to ensure job security for everybody that's currently programming. Scare people off.
Oh, there's more. Okay, I can't watch videos now. I'll never get anything done. But what I'm reading here is sort of my bread and butter, where I'm coming from all this stuff. The only thing I want to go stare at really hard here is going to be Idris and dependent types. Although I need to finish my Hindley-Milner hack because I think that's going to be fun.
Yeah, I think Idris is probably one of the more interesting dependently typed languages, because as far as I know, most of them, they're sort of in the realm of, I would say, more experimental. And Idris, I think, is trying to aim for a bit more something that you can actually use for like day-to-day stuff.
Oh, yeah.
I think like Ada and Spark, they have some hints of it. I'm not sure to what extent it's actually dependently typed, or whether it's just sort of runtime only. I think Spark actually is dependently typed. I might be wrong there.
All right. So does the main page have some reasonable reading material? I'm on the Idris website. Is there a better link?
Not sure. I think they recently also rewrote it. Not sure if the website is up to date.
I'm looking for tutorial-ish quick reads, just to get a clue as to.
Yeah, you might be able to find some on Rosetta Code, but yeah, there's no examples on the website. They have a page called Example, and it's very, very basic stuff.
Well, that's what I'm looking for. Because I'm trying to figure out the gist of what's special.
There's a FizzBuzz implementation in Idris on Rosetta Code that might be a decent start. It's nice that it actually links to it properly. 1 sec. There we go. I'll link that. Not sure if it's the best example of dependently typing it, but there's a couple more. Let's see. It's not that many examples actually of Idris, unfortunately.
So certainly the case that I can present to you the type of any expression as a compile time constant value, but I don't think that's what they're going well beyond that. Linear, okay. Wow, okay, I got some reading to do. Yeah, I will have to go stare to see, like, is there a way to efficiently execute, compute, even know what's going on? The main goals. Readable, the type's supposed to help you. So it has to be something you can tell what the hell it means in the end.
Yeah, I think that's where probably entering sort of controversial area. A lot of these sort of Haskell-based languages, at least syntax-wise, I think they like immediately get like minus 100 points for readability. I realize that's a controversial topic because I think a lot of people have different opinions, but I just look at it and just like this looks too much like Perl but worse.
There's definitely a firewall, and you're on the left or the right side.
I would imagine, you know, once you're used to it, it's probably not that big of a deal. But
right,
if you come from more like traditional syntax languages, it's a really big culture shock, I think.
Right, and I'm aiming for classic C-like syntax, except that you can write functional like stuff pretty easily without screwing around.
Yeah, I think like in terms of syntax, this might just be sort of a survivorship bias, but I think based on the sheer number of languages with common syntax, I think sort of the C-like language syntax, that's probably maybe not the best, but definitely the most approachable. And I think if you go too far, people just going to be thoroughly confused by it.
So that dependent effects example is one that impressed me particularly about Idris. It's the last link, and they show file management. And what they can express with types is state of resources, like files, for example. So you can only read a file once it is open, and the opening must have failed. So you will be forced to check whether it was successful. Also, if it is open for reading, you can only read from this, but you cannot call any write function on it, and that will be also checked at compile time. Similarly, once you have finished with the file, you have to close it. You can only close open file, and if you forget to close it, that will be also checked at compile time. So to me, it's almost like RAII on steroids. Like in C++, there is this resource acquisition is initialization thing, but this is tied to constructors and destructors. You have to acquire resource in constructor, and you have to release resource in destructor. Whereas in Idris, to my understanding, and it is a very basic understanding, but from what I can tell, you can express this arbitrarily and fully control this in types, how you want your resource protocols to work.
Okay, so Rust does memory management where you have typing system, but it doesn't have to be scoped like C++. You have to follow the lexical scope. That's
right.
The destructor, which is a fine first cut. So Rust is something more complicated. You can hand off ownership, and then somebody has to take care of it in the end. Is this somewhere in between here, or I mean, beyond that?
Yeah, so Rust uses I have to say correctly, because there's linear and affine types, and I always mix them up.
I think this part is linear, but there are affine types as well. That's true.
Yeah, either way, it's the
I
ones where the
think
types.
linear is exactly once and affine is at most once.
No, okay, I would claim Affine is something else.
Either way, the one where the type system guarantees that you can do a certain thing only once.
Yeah.
We should come up with better names for that. Yeah, so I think in this case, that's this particular example you could probably do in a affine type system. I think you could you can also do it if you have a different API. What I always think interesting with the file system APIs in languages, and I'm a bit biased here, but I think that's where you can really tell if people sort of just copied it from like another language or actually sat down and thought, hey, wait a minute. Because most languages, you open a file, the mode is like a string or an integer, something sort of nondescript. And then the thing that you get back supports all operations. You can read, write, delete, whatever. And that's how you end up with these things like, oh, you try to read, but the thing is only open for writing. Mm-hmm. And I looked into that because for Inco, the file system API is such that you get different types based on how you open things. So if you open a file read-only, you get a read-only file, and it just simply doesn't have the methods for writing or whatever. And I tried to see if there's other languages that do that. I couldn't find a single one that actually does that. They all just basically.
Idris would be one. Idris would be one,
right?
At least from this example.
Didn't know that at that time.
Did you use it any length of time to decide it was useful?
Yeah, so I actually really like it. Admittedly, I added it, so I'm a bit biased in that sense. But it's really nice because you just you get the usual benefits of static typing basically, and you don't get this weird thing where you accept the file and you have to kind of depend on somebody opening that in the right mode, and your whole thing will blow up if it doesn't. You just say, no, I want a file that supports reading or only writing or both. The thing there that I haven't really solved yet is closing and the whole disposing of things, because that's in any language that doesn't have either dependent types or affine types.
Linear.
Or linear types. Put it for any language that doesn't have something like move semantics. This is very difficult.
Yeah.
And I recently actually spent some time sort of fixing things up, because the way it used to work is because my language is built on Rust, and Rust closes files by basically discarding the whole thing. In my VM, when you would close a file, it would basically discard the underlying sort of native file object, but the managed object would stick around. But if you then try to use it as a file, you get these rather cryptic errors where it say, hey, we try to use something as a file, but it's not, because we got rid of that thing. And so I had to spend some time basically working around Rust's safety guarantees, so that it now just basically uses the close to system call. So you get still nondescript errors, but they're a little easier, because they will now say, hey, this file is actually closed, and not this is no longer a file.
Yeah, right.
And I spent some time trying to think.
But you can get this file is not closed because you still have a hook to the thing that Rust declared gone.
So there is one thing that you could do, and I think people experimented with that in Rust. Is sort of session typing approach where your file has some sort of hidden parameter with a certain type assigned to it. And when you close it, you assign a different type to it. And then all your file operations have to have some sort of extra condition that say, hey, this method is only available if that field is a certain state. And you can do that in Rust. It's, if I remember correctly, it's not the most pretty approach. If I remember correctly, basically it requires that every operation, every method has to be its own trait that you implement, because you set those bounds at the trait implementation level, which it gets really verbose. In Inco, you can set like extra bounds on the method. They apply to whatever a type parameter is inferred to. But it's sort of it's limited. I don't think you could replicate this in there. So my approach to look into that is trying to see, hey, is there a way that we can do basically move semantics, but with multiple ownership instead of single ownership as in Rust, for a bunch of different reasons. Because in theory, also that would allow you to basically get rid of a garbage collector and, you know, a bit more what's the word, deterministic memory behavior. But the sort of conclusion I ended up there was you basically end up with reference counting.
Right.
And
That's
then
what I was headed for. You're ref counting, which
there's a couple of cases through that system where you can sort of get rid of the reference counts. Like if you introduce references, you don't have to reference count those. But the moment you need shared ownership, you're going to need reference counts. And one case where that's actually very common is iterators. Because as you iterate things, the values may still be owned by whatever collection they belong to, and you're handing them out. And so you end up a case there where if you iterate over a list, for example, you can end up with these cascading reference counts just because you're iterating. And I eventually concluded there, like it's very difficult. I'm probably not smart enough to do it, and it's gonna make at least my language very different.
Yeah. There's a lot of papers on efficient ref counting, and people have gone a long way down the path of eliminating them, but it's a lot of work.
Yeah, the most efficient that I know of is RC-Imix, based on Imix. But the implementation is, as far as I understood from the paper and sort of keeping in mind how complex Imix itself already is, it's at a point where I believe you might as well implement a trace and garbage collector.
Yeah,
because
right.
their implementation, it is a little faster than tracing, but the amount of work that it needs is such that I think it's not worth the small gain that you get.
Right.
And you still have the lack of determinism and all that.
Oh, you still have a lack of determinism. They're not eagerly enough. I thought they were.
Yeah. So RC-Imix, it's essentially, for those not familiar, it's I have to say correctly, coalesced deferred reference counting plus the bump allocator from Imix, with a backup tracing collector and a cycle collection. So you essentially get the worst of all worlds for a slight performance gain.
It sounded like a final exam in comp sci.
Yeah.
So it's a really impressive setup. Don't get me wrong, and the performance benefits it gives over tracing are very very interesting. But let's say from academic point of view. But if I look at it from sort of somebody who has to implement it, and particularly already has a tracing Imix collector, I was like, no, I'll just keep mine.
Right.
Like the effort is not worth the 2-3% whatever improvement.
The gain for ref counting determinism in my head was always there was some scopable spot where I could declare the thing got freed prior to exiting, so that space was available when I re-entered.
Right.
And that would have been, if you build that one, then you got garbage collection issues, and that's the deterministic, non-deterministic leaking or whatever the hell. I don't know.
Yeah, and that's again, Rust does a decent job there. Like it has reference counting types, but it's because it's explicit and you have to explicitly tell, hey, increment. Technically it's reference counting, but I think it's like a slightly different way of doing it because it's a manual system.
Okay, you have to annotate the counts.
Yeah, so you have to explicitly say, hey, clone this thing and thus increment its reference count.
Okay.
And when you drop those types, it will decrement, and
so he
only when it reaches 0, drop it.
Okay.
So it's okay to work with. I use those types quite a bit in my VM. But it's you still have the flaws. Like you can still have cascading reference count changes and such.
Okay. What else? We're an hour and a half and all over the map. I'm going to propose we wrap it up unless somebody wants to.
I kind of wanted to add to this conversation because we've gone through a reference counting implementation as well for the memory access API, for the off-read memory access API. But we can't do lazy cleanup. We have as a requirement that we have to do deterministic cleanup. And the main problem with that we found was that you can close a segment, a memory segment, and that cleans up the resource like we want. But then how do you prevent somebody else accessing it after you've closed it, right? You can have some kind of flag in the segment itself that says, am I closed or not? But that brings up all kinds of thread safety
This
concerns.
is for NIO?
It's for the new API, so part of Project Panama, but it's sort of related to NIO.
Handing out a what's the word, a security thing, a capability, and then you turn it off at the capability level to force a layer of indirection.
Yes, exactly. So yeah, we have this flag, this Boolean flag, but because we don't want, right, you can check the flag and then do your access to the memory, but then if another flag comes in and cleans up the memory, then you're in a data race and you don't want to take a lock just to do a single memory access. So how do you solve this? We ended up solving it in two ways. One is by saying, well, you can, right, the problem is a race between an access and a close. So you can disable one or the other and then you're safe. Another way you can solve this is by saying you can only access a certain memory segment from a single thread. So an access and a close cannot happen at the same time. And then we also introduce a new synchronization primitive where you say we do the flag check, which is just a plain read, and then we do the access. And then when we do a close from a different thread, we submit a VM handshake that basically forces a full fence on every other Java thread. And then we have to be careful that we're not stopped at a safe point between the check and the actual access. So those kind of have to be atomic, and we currently solve that with stack inspection.
Can you lock the page, force the page read to trap? You'll catch the trap, declare it was on a page that was locked, removed, and therefore it was after the close, and you get whatever you get when you read after a close.
Yeah.
And then don't recycle don't recycle the virtual address for a long time.
Yes, the problem is that the virtual address space keeps being locked up for too long. Basically, we didn't try this directly, but it has been tried for direct byte buffers in the past, and basically that has been the experience. Especially if you rely on the GC to eventually unlock the page. This can become problematic if you pass down a pointer to native code or some other code, which the JDK does in some cases, for instance, to work with OS APIs. But anyways, the main point I'm trying to make is that this is a complex problem to solve if you introduce this kind of mutability. Well, really what you want is to say, I want to close this memory segment as soon as it goes out of scope, not waiting for the garbage collector. And I haven't seen a language or VM that solves something like this. Basically, you want to register a callback at the end of your lexical scope to say I want to close something, and you got to be able to make sure that the capability object doesn't leak out of your lexical scope. And I guess C++ RAII kind of works like this. Well, you could leak a pointer to a local object and then you're screwed, but they just say it's undefined behavior. So they kind of sidestep that problem. But I haven't seen any language that tries to solve this problem yet.
Well, okay, fine. I mean, finally does a horrible bad job and doesn't help you with leaking the value to another thread. So the other one is to don't put any safe points between the two loads. You have a
Yes.
load of a flag and you have a load of a native memory, and you want to load, and you don't actually fucking need a test. You want to know that you do an ordered load of the flag and an ordered load of memory, of native memory. And if native memory blows, you got your answer right there. But if native memory doesn't blow, then you look at your flag, and your flag says you're good, then you were good.
If your
So
native
you
memory
need-
broke, so you mean
need
if
no
you lost
save
the
point.
page?
You need 2 loads in a row with no save point.
Yes. So
No,
there's
you
ways
don't, because you don't. You just need 2 loads in a row with a happens before relationship between them, and then you're good. Because if the space closed, you took the exception, you caught it, you declared the space was closed after the fact, and you're done. You got the answer you get when you have a closed memory load. If the memory page got closed and then reopened, but you're on the wrong capability, your flag does the trick. So you do the 2 loads. It doesn't matter if you have a safe point between them. If the flag says you're dead, you're dead. If the exception throws you're dead, you're dead. And you just need the ordering of the flag with the native memory. So you need a volatile on the flag, for instance, and then you need the reverse when you lock it, right? You throw down the capability flag saying no, and then you volatile, and then you unmap the page. That's your happens before relationship.
volatile is already too much of a cost. We can't
Volatile
do
on
volatile.
x86 will cost you 0. You cannot. There is no cost for volatile on an x86. None.
Well, we've done benchmarks, and this slows us down by 2 or 3x. So.
You have something else going on, because
Okay.
volatile on an x86 is.
But I would still claim that if you save point in between the check and the actual access, you might be writing to somebody else's memory.
No, you don't. Oh no, I'm talking reads. If you're doing writes, then you can't let that go.
Yeah,
no,
exactly.
This doesn't work.
We've tried this with stamp locks. So basically, you get a stamp before doing the actual access, then you do the access, and then you check if the stamp was modified. This is kind of similar, but if you're doing writes, you're still corrupting somebody else's memory.
Can't do it with writes.
Yeah.
So for reads, I claim you should use a volatile, and there should not be a slowdown. I don't know where your slowdown comes from, but there should not be a slowdown, because in x86, the implementation for volatile of load volatiles is nothing at all. You get that hard guarantee from the x86 directly.
Maybe the problem was that these reads don't get hoisted out of loops anymore. I'm not sure.
They should totally, no, volatile loads will not get hoisted out of a loop, and that is the correct answer.
Yes, but we want them to hoist out of loops, because otherwise you get a liveness check on every iteration. And we want to eliminate these so you can unroll and vectorize.
Well, no, you can go ask the JIT to do unroll and jam, which it does for range check elimination for exactly the same problem, which maybe he doesn't do for volatiles. You're right. He may not unroll and jam volatile loads.
We've gone through quite a few implementations of this, and I think what we have now, right? The ultimate answer is probably to have some kind of VM or language primitive that says we cannot have a save point between these 2 things, and then we can have the check and the actual access. But right now, what we're doing is we're inspecting. I believe for every thread we stop and force the full fence on, we inspect the top 10 frames, and if the OOP of the capabilities in there, we de-optimize, and then we run it again to get the exception, I believe.
Boy, that seems overkill and underkill at the same time. Underkill because you stopped at 10 frames, and overkill because you just need to declare an exception for reading after the capability says you're closed. You don't need a de-opt.
Yeah,
There was a
reading or writing.
Needed to de-opt. I don't quite remember now. I'm sorry.
Okay, but
yeah, I think there was a problem with throwing an exception if the other thread was in a critical area. We tried async exceptions, but these were not checked everywhere. And by the way, the 10 frames are enough for the use cases we have. Basically, we annotate a top-level method, and then that declares if we're in a critical section, and then we do a bunch of calls, and then we're at most 10 frames deep, basically. The 10 frames.
Right. So you pick
I love
10 because you're demanding this code is only written by you, and so you're agreeing to only write 10 frames, which is fine.
Yes.
But it's not a capability for everybody. It's not a use case for everybody. It's a use case only for this whatever special magical trusted code base library call. You have declared that your code is in a trusted code base.
Yeah. So for solving there can be no save point in between these two. This is only in trusted code currently. Yeah.
Yeah, and both of them. Well, the 10 deep and no save point is in the trusted code. Yeah, I don't know what to do with no writes. The other another way to do the no writes is you lock, but you lock at a more expensive boundary than a single access. You hoist a lock out of a loop. If it's in your trusted code base, put the lock around a larger chunk of work. I'm about to screw around with this chunk of memory. You may not delete it out from under me. And you do your screwing around, and then you release the lock, but you screw around bulk. If you're limiting yourself to trusted code base and you have problems with super high efficiency in loops, which is common for IO, then wrap a lock around the big IO blocks.
Or the other alternative is you make the close do all the heavy lifting if it happens on a different thread.
Oh yeah, so if the close claims I'm closing and I know I'm on a wrong thread, there's some escape going on,
Yeah.
I have to find out somehow, yes.
You have to prove it on the other thread.
I have to prove it on the other threads, yeah.
Right? With some minimum number of
Well, throw down a cheat thing. So take a lock on a thread can be I set a volatile bit outside of the loop saying I'm busy here. That's the limit of my lock. And the close has to visit all threads, maybe set that bit to something or set another bit that says no, or I want to close or something. It has to do something there. And then he goes back and says, I failed because I had a thread, or there ain't no more threads and I'm good now.
Yeah, because the fast path is always I'm going to allocate it on this thread. I'm going to read on this thread. I'm going to write on this thread. I'm going to close on this thread. And, I totally agree with Jorn that nothing there can take any more than, half a clock cycle, right?
Right.
You throw the handle on another thread and it does something. Sure, it takes 10 seconds to close, but fuck you for doing it on a different thread, right?
Right.
Yeah.
Right. No, that's a.
Don't do that.
Yeah.
Doctor,
exactly.
It hurts when I push right here. The doctor says, it is a Russian joke, of course. Doctor says, don't push there.
I have my bursitis now. It's getting better. Exactly.
Don't push there.
I got this stupid pillow under my elbow right now. I'm all ready for this to be done, but they don't clean up as fast as when I was 20. So it's getting better, but it's not done yet. All right. I'm curious to see how you end up, Jorn, but I'm also going to declare, time to run.
Yeah. Okay. Well, maybe we can continue next week. Actually,
Yeah.
The thing I wanted to talk about was more how you would solve this in a language manner. But
Bring it up next week.
Okay.
Yeah. Okay. Very fun, and I see everybody next week. Have a great time, and hopefully we'll have a president next week. Oh, knock on.
I can finally close this browser tab with the blue and red map.
Unprecedented.
Unprecedented. Fine. All right. Bye.
Bye.